as hard as rocks, water ice, but there is a liquid. Liquid methane, liquid ethane. So maybe there's life. Maybe life doesn't need liquid water. Maybe life can survive on another liquid, liquid methane.
Titan's temperature is a chilly -289 degrees Fahrenheit, but it has a nitrogen-rich atmosphere which produces hydrocarbons that can stay liquid at cooler temperatures. So it's possible that Titan may be hospitable to a new type of so-called extremophile, an organism that thrives in extreme environments. In the case of Titan, they may be psychrophiles, bacteria that thrives in frigid temperatures and uses methane to produce energy. Chris McKay has observed psychrophiles under ice-covered lakes in Antarctica. Some organisms live at the bottom of these waters, where their biological activities have created a zone devoid of oxygen and rich in organic molecules like methane.
One of the interesting ecosystems in the Antarctic are the ice-covered lakes, which have a persistent ice cover of about 15 feet of ice. Below that ice, there's liquid water. Given that there's water, it's not too surprising that there's algae and bacteria living in that water.
Like Antarctica, Titan's lakes may also contain similar extreme organisms that survive on methane. And Titan may not be the only moon harboring life. In 2003, NASA's Galileo space probe snapped pictures of Jupiter's moon, Europa. Evidence suggests liquid water may exist underneath its frozen crust. Scientists think Europa has an ocean that's over 50 miles deep. There are also signs of volcanic activity. So Europa's icy water could be warmed to a liquid state by volcanic vents on the ocean floor. And this volcanic activity would aid in cooking up chemicals necessary for life.
We have very convincing evidence that below the icy surface, there's an ocean. Ocean, water, maybe life. And we also have evidence that there are possible energy sources in Europa. So all the necessary ingredients for life seem to be there.
The ice on the surface of Europa is extremely thick, maybe as much as 6 miles deep. So it is unlikely that a human spacecraft will be able to drill down into its ocean anytime soon.
I think a realistic mission to Europa would be to search the surface for evidence of organisms that have been carried up through the cracks and deposited on the surface. They would be dead, but they would be biological and we could study them.
Our solar system is full of diverse, interesting places, and we shouldn't rule any of them out for life until we explore broadly, because we don't really know what we're looking for.
Armed with new technologies, astrobiologists have widened their search for extraterrestrial life. The next frontier includes our entire Milky Way galaxy and beyond. Astrobiology is pushing back the boundaries of modern science. Researchers now have the technological instruments to locate exoplanets. These are planets that exist outside our solar system. Exoplanets need to pass several tests in order to be considered suitable for Earth-like life. Most importantly, they need to be within a habitable zone of a central star like our Sun in order to support liquid water.
Our star is just right. It's not too hot and it's not too cold. And so we're just right in this perfect area where life was able to evolve.
In 2008, NASA plans to launch a space telescope called Kepler to search for terrestrial Earth-sized planets. The spacecraft's instruments will be able to detect exoplanets by measuring changes in a star's light curve as a planet passes between the star and the spacecraft. Jeff Marcy is one of the world's leading planet hunters.
We would estimate that there are some 50 billion, maybe 60 billion Earth-like planets within just our Milky Way galaxy alone. And remember, our Milky Way galaxy is just one of hundreds of billions of galaxies out there, more or less like our Milky Way. So the number of Earth-like planets in our universe is a nearly uncountable number.
But locating exoplanets is only half the battle for an astrobiologist. In the next 20 years, NASA will launch the Terrestrial Planet Finder. This collection of highly sensitive space telescopes will actually recognize if a planet has the right atmospheric gases, such as water vapor, carbon dioxide, methane, and ozone, all necessary to sustain Earth-like life.
With that picture, we can then take the light from that planet, spread it out into all of its colors or wavelengths, blue, green, yellow, red, even into the infrared, and analyze that light for the chemical composition, maybe even the biological composition of that planet. What we might find are signs of life in a variety of forms. For example, oxygen.
When it comes to producing larger Earth-like life, a planet or moon needs oxygen. 3.4 billion years ago, the only life on our planet were single-celled microbial organisms. But as this primitive life absorbed energy from the sun, it formed a green pigment called chlorophyll. This produced photosynthesis, a chemical process which converts carbon dioxide and water into energy, with oxygen as a waste product. Single-celled organisms evolved into cyanobacteria, one of the Earth's earliest structures. Cyanobacteria injected vast amounts of oxygen into the oceans and air. New life emerged, which diversified and developed into large multicellular species, and eventually, man.
Our Earth would not have oxygen in the atmosphere if it were not for plant life, by photosynthesis generating the oxygen that otherwise would oxidize rocks and vanish. So oxygen is a biomarker for the Earth. If we could examine another Earth-like planet and detect oxygen in its atmosphere, it would be one key sign, not yet definitive, but one element of the argument that that planet too has photosynthetic life.
At NASA's Ames Research Center, astrochemist Lee Bebout and her colleagues are cultivating oxygen-bearing ecosystems in a greenhouse. They're microbial mats, complex microbe communities often found on muddy and sandy sediment surfaces, in hyper-salty waters and carbonate beaches.